Okay, I think we're recording. So, any questions? Remember how this review session goes. You guys ask questions, I answer them until we're finished.
Can you explain for ring opening polymerizations, what is the graph like for molecular weight versus time?
Good question. So, what do you guys think? For ring opening polymerizations, what type of polymerization is it? What do you think? Step growth? How can you guess step growth? Why is that a good educated guess? So go ahead, Zach.
There's going to be multiple steps to opening up the ring and then joining it to the longer.
So one ring has to join to another ring, has to join to another, and there are no what? You're close. There's no double bonds, right? And so we know that, so if we have, say, ring opening polymerization of caprolactone or something like that. I think it's like this. And so this will open and we'll get some sort of polyester from this, or caprolactone. 1, 2, 3, 4, 5, 6, not quite. 1, 2, 5, 6, 7. There we go. And so there's no double bonds or multiple. So no chain growth. So this ring opening polymerization proceeds through dimer, trimer, etc. And so that's indicative of a step growth. And so now what's the molecular weight as a function of time or as a function of conversion for step growth polymerization? Right? We need to get to high conversion in order to get high molecular weight. So we have Mn as a function of time. And so we need high conversion for high Mn. And so the key here is really the no double or multiple bonds. So all of the chain growth mechanisms that we've studied have multiple bonds in them. And so if you don't see any multiple bonds, you can pretty much guess that it's going to be a step growth mechanism or something, something that's not chain growth. Is that cool, Light? Yeah. So we haven't studied exactly how these rings open. We'll study that when we get to polyesters. We'll study it when we get to polyamides. What are those different monomers? How do they polymerize? But for now, step growth versus chain growth, that basic mechanism is what you want to know. Is that cool? Okay. Next question.
For homework number 4.
Well, hold up. Sorry, like 1 sec. So what if I gave you this monomer? This is a good one. What if I gave you cyclooctene? Does anyone remember, does anyone know what cyclooctene is? Octene, how many carbons?
8.
8. Cyclo?
A ring.
Ring. So we have to draw an octagon, right? Octene.
1 double bond.
So if we polymerize this thing, what is the mechanism going to be? What do you think? Does this ring open?
No.
You can guess maybe not. but it will polymerize through this multiple bond. Maybe if we add ethylene,
Just gonna make a bridge, right?
it's going to make a cyclic inside the ring. And so you'll have something that looks like this, and then you'll have this thing right here, and then it'll keep going. So you can make cyclics inside of the ring because this will polymerize with ethane. And so I think that's a slide in your one of the note sets where you can make cyclics in the chain. Now if we have, say, let's see, this is 1, 2, 3, 4, 5, 1,5-dioctene, right? Then we can have polymerization through both of those multiple bonds, so you can get some unsaturation in the chain. So that's just sort of an aside, but it's something to remember that just because it's cyclic doesn't mean that we can't polymerize through the multiple bonds. Okay, so go ahead, Leigh, ask your question about homework number 4 now.
For question number 2, so for well, probably it's not a good question, but can you explain again the answer for the LDP and HDP? I mean, yeah.
Sure. So low density polyethylene. What does the chain look like for low density polyethylene? Why is it low density? Highly branched, right? So why is it low density? What's the crystallinity like? Zach?
Branches create a lot of free volume so that it can't crystallize. The chains can't hold on themselves very easily.
Branches can't fit in crystals, right? So branching decreases crystallinity. Good, so branching decreases crystallinity always, and so if it has low crystallinity, equals low density. What's the mechanical strength of a low density polyethylene? Relatively low. It's going to be a little bit more flexible in the range of 10 to 20 MPa, right? And so in order to get branching, we know that LDPE is made at high pressure under free radical conditions. So that's in Chung's course manual if you read about LDPE. And so they put in a lot of free radical initiators. They create radicals on the chain, and that causes branching. So for high density polyethylene, what does it look like? What's the chain look like? Just a few branches, right? So just a couple branches. So we have a few branches. Equals high crystallinity. Equals high density. And it's got a modulus of 20 to 30 MPa. Excuse me. And so, high density polyethylene, how is it made? Ziegler-Natta, right? Ziegler-Natta is a more controlled polymerization than free radicals, so we're not creating branching sites on the chain using this Ziegler-Natta coordination. And it's made at benign pressures and pretty, low pressure and pretty benign temperature. But the idea of branches versus no branches and that controlling the crystallinity, the density, and the mechanical properties is the important part of this. What's the approximate percent crystallinity for high density polyethylene?
60 to 75.
60 to 75, good. Low density polyethylene?
40.
40 to 50, something in that range. And so the crystallinity isn't that much different, right? But it has a huge difference in mechanical properties. Are crystals more dense than amorphous? Yes. What's the glass transition temperature of polyethylene? Minus 120, something like that. So is amorphous polyethylene rubbery or is it glassy at room temperature? Rubbery. So it's got a really rubbery phase in it. So the amorphous phase is really rubbery. That gives it some impact strength, right? That's why you can bend the plastic without cracking it. But the crystals hold together the material. And so that's why it seems like a solid at room temperature, because those crystals are holding everything together. What's the approximate TM of polyethylene? 100, 110, somewhere in there. It depends on crystallinity. It can be a little bit higher, but yeah, it's heat-resistant plastic, right? So you have to get to pretty warm temperatures before you melt all those crystals. Yes?
We can get LDP using Ziegler-Natta too, right?
So, I mean, you need to create some branching somehow. And so free radical initiation is the easiest way to get the branching. What type of low-density polyethylene can you make with Ziegler-Natta? There's a special type. Linear low density. And so what does linear low density look like? Linear low density polyethylene. Regular short chain branches, right? Where do the short chain branches come from? The alpha olefin content that we use in the linear low density polyethylene synthesis with Ziegler-Natta. So when you go out in the real world, linear low density polyethylene is different than low density polyethylene. So the type of branching also makes a big difference. And so people like linear low density because it's more controlled synthesis. It actually flows easier because of these short chain branches. Long chain branches make low density polyethylene difficult to flow. And linear low density polyethylene is a more repeatable synthesis because you're adding comonomers repeatedly. So remember, linear low is different than low. It's made differently, it's got different properties, it's used for different stuff. The chains look different, the chemistry is different, and so make sure that you know the difference. So low density polyethylene is this, linear low is this. Any other questions on polyethylenes?
So for HDP, is it wrong to say, like, if I use the single site coordination catalyst for the synthesis, is that wrong?
No, so you can use metallocene. So you can use single site for this, you can use single site for LLDPE. In fact, a lot of technology is switching from Ziegler-Natta to metallocene. But you can't make low density polyethylene with metallocene catalyst because you can't get the branches. And so because the branching is either non-existent or because the branching is very controlled, you can use metallocene catalyst for these two polymers. Depends on the patent, depends on what technology your company owns. But the only way you can get the branches is by free radical polymerization. Yes?
Is it the pressure for HDPE to 20?
So this is a modulus.
Modulus.
So this is modulus. And so HDPE is on the order of 20 to 30 MPa modulus, or yield strength. Make sure the camera's going here. Looks good. Great. Let me pause it to make sure that something's happening.